Hello, welcome to another Further Maths video on vectors, where today we're going to be using the cross product to help us work out the areas of shapes. And to do that, we're going to be exploiting a property of the cross product that we did first introduce in my first video covering the cross product, which is this property here. However, in that video I did mention that this formula isn't used that often when trying to find the cross product because the information you usually have about vectors makes one of the other approaches more easy to do. However, it is going to be useful for what we're doing today because parts of this formula seem rather familiar. Because, for instance, we've got the magnitude of the vector A times by the magnitude of the vector B, and as a reminder, a magnitude of a vector is kind of similar to the length of that vector. And then we're multiplying that by sine of theta, where theta is the angle between the two vectors. So, wait a minute, we've got a length times by another length times by sine of the angle in between those two lines. Doesn't that seem rather similar to the formula for the area of a triangle, half AB sine C? Okay, I mean there's a few differences. Obviously, namely, to begin with we don't have that half out the front. But the other aspect is we have that n hat on the end of this formula that obviously we aren't used to seeing as part of half AB sine C. And that n hat is there because when we do the cross product of two vectors, you get a vector as the result, not just a single number. But can we make any alterations to this formula so that it starts giving out the result as just a scalar number rather than a vector? Well, yes. We could, for instance, take the magnitude of the cross product of vectors A and B, because that means we'd take the magnitude of everything we see on the right hand side of the formula. And that means we would get the magnitude of A and the magnitude of B still as normal because they already were magnitudes, so taking the magnitude of them again won't have any effect on them. But we would also be having to take the magnitude of sine theta and the magnitude of n hat. But won't taking the magnitude of these things affect what we've calculated? Well, actually yes, but in a good way. Because you see, if you're looking at a triangle, the angles in a triangle are guaranteed to be between 0 and 180 degrees. And the reason that's interesting is that therefore sine theta is guaranteed to be bigger than 0. And that's interesting because if you take the modulus of a positive number, it has no effect on it. You just get the same positive number as an output. So therefore the magnitude of sine theta is just going to be sine theta. So therefore so far we've got modulus of A, modulus of B, times by just sine theta as if that modulus sign isn't there. And then lastly we're taking the magnitude of n hat. But n hat is a unit vector. And therefore, by definition, as a reminder, any unit vector always has a magnitude of 1. So we are just multiplying by 1, which of course is just going to be magnitude of A, magnitude of B, sine theta. But therefore, if we want to utilize this result to work out the area of a triangle, we've just got to include that final missing thing from the formula half AB sine C, which is that scale factor of a half. So therefore, the area of a triangle is defined as being half lots of the magnitude of the vectors A cross product with the vector B, where the vectors A and B are representing two of the edges of the triangle. I must stress that it is the edges of the triangle, not the corners, not the vertices, the lines, the edges themselves. And I'd also like to point out that personally, when I do this stuff, I always make my vectors A and vectors B be two edges coming out of the same vertex on the triangle. This doesn't actually have to be true in order for the formula to work, as long as vector A and vector B are any two edges on the triangle. It's just that if you do it this particular way, it's going to be helpful for some of the other different things we're going to be doing in the future with vectors. So that's something to bear in mind. Sadly, this is a formula that's not in the formula booklet, so it's one you're going to have to remember off by heart for the exam. But now that we've learnt the formula, let's use it in an example. So we've been given a triangle with vertices with the following three coordinates, and we've got to find the area of the triangle. And to help us do that, we do have to bear in mind that we've been given the coordinates, which means we have the position vectors of the vertices, but we can't use any of these numbers directly as the vector A or the vector B in the form we were looking at before, because the vector A and the vector B had to be the edges. So therefore, to help us do that, let's draw a diagram. Because we're dealing with 3D, I'm not too bothered about exactly where each of these coordinates are while I'm drawing my diagram, and instead the diagram's more for just being able to see what's connected to what and what information I have. So therefore I'm just going to draw 3 points and label them 1, 2, 3 as the first one, the second one 4, 3, minus 1, and then the third one we might draw down here, 2, minus 9, 0. We're then connecting up these points to form the edges of our triangle. So therefore this is what our triangle looks like. But as I already mentioned, these numbers we see currently are not the vector A or the vector B, because those have got to be the vectors for the edges, so that's what we've now got to calculate. And to work out those edges, we're just going to make use of the fact that these coordinates are effectively giving us the position vectors, which as a reminder are just a vector taking us from the origin O to each of these points in turn. So therefore the position vectors are this vector here, and this vector here. Sorry for the not so straight lines. But therefore if I want to, for instance, calculate the edge of the triangle that's over here, then let's say I'm going from 1, 2, 3 to 4, 3, minus 1. That would of course be calculated by going backwards down the position vector for 1, 2, 3 to get from 1, 2, 3 to the origin, and then forwards down the position vector of 4, 3, minus 1. In other words, we're doing 4, 3, minus 1 minus 1, 2, 3. And if you subtract those two vectors, you will get the vector 3, 1, minus 4. So that's the first vector for an edge on our triangle. And you don't have to do it this way, but as I mentioned on the previous screen, I do prefer to have both my vectors coming out of the same vertex of the triangle. So given what I've chosen as my first edge, that means therefore the second edge I'm going to be using would be this one here, going from 1, 2, 3 towards 2, minus 9, 0. And therefore calculating what that vector would be is just going to once again be subtracting the position vectors the correct way around, which would be this. And that will come to 1, minus 11, minus 3. And so if I want to calculate the area of the triangle, I know I'm just now going to need the cross product of the vectors for these two edges. So therefore I'm now going to calculate that. So we've got 3, 1, minus 4 cross product with 1, minus 11, minus 3, if I can say it. So therefore that would be I, J, K, 3, 1, minus 4, 1, minus 11, minus 3, and the magnitude of that 3 by 3 matrix will give me the cross product. So therefore that's going to be minus 3 minus 44. We're going to have minus 1 lots of, minus 9, minus 4, and then lastly we're going to have minus 33 minus 1, which means our cross product is just simply minus 47, positive 5, and minus 34. And if we therefore now want to work out the area of the triangle, all we've got to do is realise it's going to be half lots of the magnitude of this vector. So it's going to be half lots of the magnitude of minus 47, 5, minus 34, which of course would just be half lots of the square root of 47 squared plus 5 squared plus 34 squared. If you work that out, that will come to 1/2 lots of the square root of 3,390, which comes to, if we're writing it as just one decimal, 29.1 to 3 significant figures. In this question, they didn't have any units specified, so I'm not going to have to write any units for my answer, but that is something to watch out for that sometimes gets people caught out. If they say centimeters, then your answer would have to be centimeters squared, of course. But the fun doesn't have to just stop there. If we've got not just one triangle, but two identical triangles, we can paste them together, and that will get you a parallelogram. And therefore that means that the area of a parallelogram is always just going to be double the area of a triangle. And therefore we can take the formula for area of a triangle and double it. So therefore the area of a parallelogram is given by the formula, the magnitude of A cross product with B, where A and B are once again the vectors for the edges of the parallelogram, and as before, I generally like to make these two vectors coming out of the same point, not because you have to, but because of other things we're going to be doing later with vectors. So there you go, it's as simple as that, although it is worth mentioning once again that this formula is not in the formula booklet too. So let's launch into a second example. We've got the 4 points A, B, C and D, and we've got their coordinates, and we need to find the area of the parallelogram ABCD in exact form. Something bearing in mind that when they write it like this, ABCD, with the letters referring to the vertices, they're giving you a clue as to which corners are connected to which corners to form the shape. So when they say ABCD, it means our parallelogram potentially looks something like this, where we've got A connected to B, B connected to C, C connected to D, and therefore by logic D must be connected back up to A again. And this is important because it means it affects what coordinates we combine with each other to work our edges. For instance, we can't connect up A and C because that isn't one of the edges of the parallelogram. So therefore instead I'm going to, for instance, choose to do A to B and A to D. So therefore AB as a vector, well, once again we've just got to subtract the position vectors the right way around. So that would be the position vector of B, take away the position vector of A. So therefore that would be that, which conveniently comes to 1, 2, 3, almost as if I designed this example to do that. And then we've got the other vector we're trying to find, AD, and therefore I am going to do D, or the position vector of D I should say, take away the position vector of A. And if you work that out, that will come to 2, 3, minus 5. And so therefore now that I have the vectors for the edges, I can work out the cross product. So that's just the cross product of 1, 2, 3 and 2, 3 minus 5, which again would be doing I, J, K, 1, 2, 3, 2, 3 minus 5. And if you work out what that comes to, that will come to 19, 1 minus 7. Saving some time by skipping some of the calculation there. But the point is, to finish off the question, the area of the parallelogram is going to be even more simple than before. It's literally just going to be the magnitude of that vector, so that's going to be the square root of 19 squared plus 1 squared plus technically minus 7 squared. And so therefore, if you work that out in exact form, that will come to the square root of 411. And there you go, that's all I wanted to cover today. Something to watch out for though is that they can sometimes put these questions in a context, and therefore you do have to watch out for, as already mentioned, things like units, but also as part of a part B or part C question, they might ask you to do other things, such as combine area as part of other calculations, such as, I don't know, for instance, reusing the formula for pressure that you learnt at GCSE. So do watch out when those types of things do crop up. See you in a future video. Goodbye.